Hello everyone, my name is Matt and welcome back to Physics Calculus. Today I'm going to be solving a projectile motion problem for you guys. So this problem is adapted from Chapter 3, Problem 47 from University Physics, and it says, a pilot flying a plane horizontally at 70 meters per second and at a height of 83.0 meters above the ground drops a payload, hoping to hit a target on the ground below. How far should the pilot be horizontally from the target when he releases the payload? Air resistance is negligible. Okay, so since this is a projectile motion problem, let's draw a picture here. So we have a pilot flying a plane. Here's my plane. And he's flying it horizontally at 70.0 meters per second. And his height above the ground, we're told, is 83.0 meters. And he's trying to drop a payload on a target right here. So it's going to go like this. And we want to know how far horizontally he should be from the target when he drops the payload. So this is going to be the distance that we're looking for, what I'm going to label dx. Okay, so I'm going to define my coordinate axes here real quick. So this is going to be my positive y direction, and this is going to be my positive x direction. And this is going to be y sub I, and this is going to be just y. Okay, so whenever we're solving a projectile motion problem, what we want to do is make a table. One column for the x direction, one column for the y direction, so we can list our givens. So this is going to be my x column, and this is going to be my y column. And this basically just shows that these are my givens for the x direction of the motion, and these are going to be my givens for the y direction of the motion. So I'm going to write vi, initial velocity, vf for final velocity, a for acceleration, d for distance, and t for time. So let's put in our givens here. So we're given that the initial velocity in the x direction right here is 70.0 meters per second. So this is going to be 70.0 meters per second. And in the y direction, well, the x and y motions are independent, and the y direction in the y direction, the initial velocity of the payload is going to be 0 because it's not moving relative to the plane in the y direction, or relative to the ground in the y direction. So this up here is going to be 0. And for the final velocity, well, it's not accelerating in the x direction. It's not accelerating in the x direction, so my final velocity is going to be the same as my initial velocity for the x direction. So I'm just going to put a bar there showing that these two are the same. And for the final velocity in the y direction, well, it's going to be accelerating, so it's going to be different than the initial velocity in the y direction, but we don't know what it is yet, so I'm going to leave that blank. So for the acceleration for the x direction, we know that that's going to be 0 because it's not accelerating in the x direction. But for the y direction, it's going to experience gravitational acceleration, so this is going to be negative 9.80 meters per second squared. So for the d value for the x direction, this is what we're trying to find, right? Because we're trying to find dx, so I'm going to just put a question mark there because that's what we're trying to find. And then for the y direction, we know this is 83.0 meters, and so we have y minus yi, so this is going to be 0 minus 83.0 meters. So for our d direction, we have negative 83.0 meters because it's traveling in a negative y direction. And our time, well, we don't know what the time is yet, but we know that it has to be the same for both the x and the y components. So I'm just going to leave that blank for now. Okay, so how do we go about solving this here? Well, as I just mentioned, we know that this time t has to be the same, and we only have about two variables here because vi and vf are the same, so we have two separate ones here, so that's not enough to solve for time. But we have three over here, so what I'm going to do is I'm going to use the y direction, what we know in the y direction, to solve for time. And then we know that has to be the same for the x direction, so then I'm going to use time plus our other givens over here in the x direction to solve for d. So let's go about solving for time here. So which equation should we use? Well, we know the distance in the y direction, we know the acceleration in the y direction, we know the initial velocity in the y direction. So I'm going to use the equation y minus yi equals vi sub y t plus 1/2 a sub y t squared. And as a quick side note here, our vi is going to be 0 because we have no initial velocity in the y direction. So that's initially going to be 0. So this term goes away. However, if we had a non-zero initial velocity in the y direction and we were solving for time, then we'd have to use the quadratic formula. But fortunately, that is not the case here because this term is 0. So we have y minus yi, which is essentially just d sub y, equals 1/2 a sub y t squared. Okay, so let's solve for t here. I'm going to multiply by 2 on both sides and divide by a sub y, and then take the square root of everything. Let's raise all this to the 1/2 because a fractional exponent gives you a root. So this is going to be 2 times y minus yi divided by a sub y, and then we take the square root of that to get t. Okay, so let's plug in some numbers here. So we have 2 times y minus yi, which is d sub y, which is negative 83.0 meters, and negative 83.0, divided by acceleration in the y direction, which is negative 9.80. Alright, so let me just calculate this real quick. Okay, so I got 4.1157 seconds for the time that it takes to fall. So this is 4.1157 seconds, and this also is 4.1157 seconds, because they have to be the same. So now we know the time that it takes for it to fall. So we have enough variables over here. We have enough knowns over here to solve for dx. So how do we do that? Well, because there's no acceleration in the x direction, and because the final velocity is the same, velocity is constant for the x direction, we can just use v equals d over t. So applying this to the x direction, we have v sub x equals d sub x over t. And solving for d sub x, which is what we want, multiplying by t on both sides, we have v sub xt equals d sub x. So let's just make sure that this is going to give us correct units. This is in meters per second, and this is in seconds, so this is going to be in meters, so that's good. Our dimensional analysis works out. So let's plug in the numbers here. We have 70 meters per second here, and then for t we have 4.1157 seconds. Alright, so let me just punch this into the calculator real quick. So I got 288.099 meters for dx. And rounding that to 3 significant figures, because we have 3 significant figures in our problem, we have 288 meters for dx. So this is our final answer for this problem. The pilot should release the payload at about 288 meters from the target that he wants to hit. Thank you guys for watching. I hope you enjoyed this video, and I will be back next weekend with more physics problems. Thank you.